This video covers notes 19.1 over simplifying radical expressions. So the first thing we're going to do is refresh our memories on how we simplify square roots, because we did this back in the fall. So for number 1, when you simplify the square root of 200, the first thing you want to do is check your calculator. Now, in my calculator, I can see this does not work out to be a nice number, so this is where I create my factor trees. Remember, with factor trees, we start with like a 2, a 3, a 4. You can pick whatever number you want, but we're looking for numbers that divide evenly. So 2 is the same thing as 2 times 100. 2 cannot be broken down anymore, but 100 can. So if we try 100, we could do 2 and 50. Maybe you're thinking a little bit bigger and you remember that 100 is 10 times 10. So you could stop there because we are looking for pairs. If you wanted to, you could go all the way down to 2 and 5 and 2 and 5, and then you would just take out 2's and 5's. So the square root of 200 is the same thing as 2 times 10 times 10. Remember, in order to get out of the square root, you are looking for a pair. So the 10's go outside and we write it one time, and the 2 will stay inside. To check your work, you can do the square root of 200 and compare the decimals to the answer that you got, and these decimals are the same. So for number 3, again, check every single one of them in the calculator. When we go through the notes, I know the ones that will work and the ones that don't, so I might not check all of them, but you should check all of them first. Now, I see it does not work nicely, so 54, you could start with 2, you could start with 3. Maybe you catch that 6 and 9, make 54. 6 is 2 times 3. Remember, we're multiplying always. We are not adding. 9 is 3 times 3. So I will rewrite this. There's a negative 3 out front, and then 2 times 3 times 3 times 3. And remember, you can check that as well to make sure you get back to that 54, still under the square root. Now I'm looking for a pair, so there's a negative 3 out front, and a set of 3's that's going to go outside, and then a 2 and a 3 that are going to stay inside. Remember, when you take the square root of 3 times 3, if you plug it into your calculator, when you go outside of the square root, you only write one number. You need a pair to get out, but you only write it one time. Now, once they're outside, they can hang out together. So negative 3 and 3 come together to make 9. And then our friends inside can, I don't know, play video games or something inside. So the 2 and the 3 can hang out together. And so that is my simplified answer. And if we double check, I have the same decimals. So we're going to look at some letter examples and try to come up with a pattern, and then apply the letters to what we're doing here. So a squared is a times a. So under the square root, we have a times a. In order to get out of this square root, you need a pair. So the square root of a squared would just be the letter a with nothing left on the inside. A to the 3 is a times a times a. So you can take out a group of 2. So we would take out one of the a's, and we would have one left. A to the 4 is a times itself 4 times. You need a group of 2 to get outside, so we have 2 groups of 2. So I would have a squared, so 2 groups of 2 get to go outside, and a times a is a squared. Hopefully you're starting to see a pattern here. A to the 5th, we have a 5 times, so we can take out 2 groups, and we would have one little friend left on the inside. A to the 6th, we have 6 a's. So we have 1, 2, 3 full groups and nothing left on the inside. And then a to the 7, we would have a 7 times. So we have 1, 2, 3 groups, and then we have one friend who's left on the inside. So hopefully you're seeing a pattern, and it kind of has to deal with evens and odds. So if you notice, every time we didn't have a square root left over, it was because we had even exponents. So this example, and this example, we had even exponents. We took the exponent and divided by 2. And then from there, whatever number we got, that equaled our exponents on the outside. So then for our odd exponents, those are happening here, here, and here. We still divide by 2. And then the number goes outside. And we'll always have 1 left on the inside. Because remember, we're looking for pairs. We're looking for groups of 2. So if they're even numbers, they divide evenly into nice, pretty groups of 2. If they're odd numbers, we're seeing how many groups of 2 can I make, and there's always going to be 1 friend left over. You will never have more than 1 friend left over on these problems. So instead of writing out A 24 times, let's divide by 2. That's a nice, pretty number, so we have A to the 12. We can take 24 and put it into 12 groups of 2. For number 8, 31 divided by 2 gives us 15.5. So that means we can make 15 pretty groups of 2, and the 0.5 tells us we are going to have a leftover, a remainder. So that's our friend that's left on the inside. Number 9, we take 40 divided by 2. We can make 20 groups of 2. 47 divided by 2. We can make 23 groups of 2. And the 0.5 tells me that I can't make nice, pretty groups, so I'm going to have 1 left in the square root. For number 11, 120 divided by 2 is 60. That works out nicely, so they're all going to get out of the square root. 101 divided by 2 for number 12 is going to be 50 nice sets of square roots and 1 remainder. So anytime you see a 0.5, the big number goes on the outside and there's 1 left on the inside. So when we're simplifying these problems, number 13, remember we always want to start with the square root in the calculator. Oh, look, how nice. The square root of 144 is 12. And then for the y's, we do 2 divided by 2, and we get 1. It's a nice, pretty number, and so all of that goes on the outside. You can make 1 full group of 2 exponents. Number 14, check that square root first. Oh, look, the square root of 81 is 9. And then for my exponents, I'll take 4 and divide it by 2, 6 and divide it by 2, and 10 and divide it by 2. So for the A's, I have 2 full sets. For the B's, I have 3 full sets. And for the C's, I have 5 full sets. None of these have remainders, so there will be nothing left under the square root. Number 15, when I check the square root of 24, it does not work nicely. So 24 is 2 times 12. You could also do 3 and 8. You could also do 4 and 6, completely up to you. 12 is 4 and 3. You could also do 2 and 6. And 4 is 2 and 2. So remember, these are all of my leaves of my factor tree. If I double check, 2, 2, 2, and 3 will get me back to 24. So I have 2, 2, 2, and 3 left under the square root. I have a group of 2's, so those 2's will come outside, and then the 2 and the 3 left on the inside will make 6. I'm going to figure out what's going on with my letters and then put all of it together, kind of like we did with the other exponents unit. So x, I take 5 and I divide it by 2, and I get 2.5. So that means 2 are going to go on the outside. 0.5 means I have a remainder. So now I'm going to take this answer and put it all together. Outside, I have a 2 and an x squared. On the inside, I have a 6 and an x. Now, I didn't show it, but one thing you should have done is compare your decimals for the square root of 24 and 2 square roots of 6. Make sure you get the same decimals. Number 16, I checked the square root of 75, and it does not work nicely. 75 ends in a 5, so I'm going to see, and yes, it is divisible by 5. 15 is 5 and 3, so I have 3, 5, and 5. And that would get me back to 75. I have a group of 5s, a group of 2, and then a 3 that will stay in the square root. So to check real quick, square root of 75, 5 square roots of 3, same decimals. For my letters, x squared, we do 2 divided by 2, and we get 1, meaning they're all going to come out of the square root because they all have a nice group of 2. Y's, we do 3 divided by 2, and we get 1.5. So that means 1 is going on the outside. 0.5 means there's a remainder. Put all of it together. Outside, I have a 5, an x, and a y. On the inside, I have a 3 and a y. Remember, if you have even exponents, you should not have any of those letters left under the square root. If you have odd exponents, there should be something left under the square root. If you have numbers under the square root, that means when you plugged in your original, it did not work out nicely. So last two, the square root of 128. Man, that's a big number. Let me check. Oh, dang it. So 128, I start with 2. 2 and 64 works. You could also try, like, if 2 works, try 4. If 4 works, try 6, stuff like that. 64, I notice, is the same thing as 8 times 8. Remember, we're looking for groups of 2. So one thing you can do is stop when you get a pair. Even though you could continue breaking down 8s, you're looking for groups of 2. So it's okay if those groups of 2 are bigger numbers. So we have 2 times 8 times 8. So the 8 will go outside and join that negative that was there. And the 2 will stay inside. If I do a quick check, negative square root 128 and negative 8 square root 2, same decimals. And then if I look at my exponents, my a's, I have 1 divided by 2, and that's going to be a 0.5, so that one's not going to go anywhere. B, I have 1 divided by 2, that's also a 0.5. So if you notice, because these exponents are 1, there are no groups of 2 for them to go outside of the house with, so they're going to be stuck under there. So the only thing that's coming out is that negative 8, and then we have a 2, a, and a b. Remember, the 0.5 just tells us we leave 1 under the square root because we don't have a full group of 2. And then for number 18, if I check the square root of 32, it does not work nicely. So 32 is 4 times 8. 8 is 2 times 4. So I have 2 groups of 4. I could stop here. So if I just use my numbers, there was already a 3. So I'm going to keep that 3 out. I'm going to take out a 4. And then 2 is going to stay inside the square root. So I would end up with 12 square roots of 2. So if I compare my big numbers, 3 square roots of 32 and 12 square roots of 2 both work to the same letters. Then let me look at the square roots first. Inside, I have 13 a's. When I divide by 2, I can make 6.5 groups. So that would be 6 on the outside, 1 that is left on the inside. B's, I have 14 divided into groups of 2. So I can make 7 full groups. Now, one last thing to notice before we put all of this together. This color. There was already an a squared on the outside. So when I take a to the 6 and combine it with a to the 2, there will really be a total of a to the 8 because there were already 2 and we're bringing 6 out. So my final answer altogether, I have a 12 on the outside, 8 a's, and 7 b's, and then I have a 2 left on the inside and an a left on the inside. There are no b's left on the inside because those exponents were even.